All right, so let's continue with 3.1 here, and let's do a couple of examples of finding the relative extrema of a function of x. All right, yeah, as mentioned last video, the relative extrema, we have two types, relative max or relative min. And these two represent either the highest point or the lowest point of a function relative to neighboring values. In other words, the relative max represents the point in which our function changes from an increasing to a decreasing behavior. And the relative minimum is the point in which our function of x changes from a decreasing behavior to an increasing behavior. And we can determine that change of behavior based on the values of the first derivative, based on the values of the slope, the rate of change of that function. All right, so for this first example, let's find the relative extrema of our function of x, defined as, say, x cubed. Let's sort of cube one. Not sort of cube one. X cubed minus 6x squared minus 15x plus 30. All right. Now, to find the relative extrema, to find the relative max or min or to find the relative max or min of a function, we have to first find their critical numbers. And in order to find the critical numbers of the original function, we have to first find the derivative. So first step, let's find the first derivative here. I'll use a different color. So using the rules from chapter 2, let's find the first derivative of this function, right, which is in this case just a polynomial function. So let's find the derivative of each individual term. Derivative of x cubed, well, that's just going to be, oh, not that. It's going to be 3x squared. Derivative minus derivative of 6x squared, bring the power down, multiply the coefficients, decrease the power by 1 to give us 12x. And a derivative of negative 15x, well, the derivative of a coefficient attached to just a first power of x is just that coefficient, so minus 15. And derivative of 30, derivative of a constant with no variable attached, that's just 0. Okay, so first step, find the first derivative. Second step, take that first derivative and set it equal to 0. In other words, we want to figure out, we want to find the critical points, we want to find the values of x in which the slope will be 0 for our original function. So second step, set the first derivative, f prime of x, equal to 0 and solve for x. All right, so here we're going to take our first derivative, which we found to be 3x squared minus 12x minus 15. Set this equal to 0. Now, before we start solving for 0, let's see if we can take out any common factors between our three terms here. Look at what we have. We have 3, 12, 15. What do these three coefficients have in common? A factor of 3. So let's take 3 out from each term to give us x squared minus 4x minus 5 on the inside. All right, and now let's factor out this quadratic here on the inside to give us 3 times. Let's see, x squared minus 4x minus 5. This factors out into x minus 5 times x plus 1. Okay, equal to 0. All right. And then what we do, again, just like in algebra, after we completely have factored out our equation, then set each factor that involves x equal to 0 and solve for x. Meaning we're going to set x minus 5 equal to 0, and x plus 1 equal to 0. Again, any factor that involves x within its expression. And solving for x, for each of these two equations, we have that x is going to equal 5 or -1. Meaning that if we plug in 5 or if we plug in -1 into our first derivative, it's going to give us 0. Meaning at these two x coordinates for the original function, at these two x coordinates, the slope will be 0. All right. So these 2 points of 5, -1 are representing our critical numbers, which I'll denote as Cn from here on out. All right, so critical numbers, Cn. Okay, but we're not finished. The question that it just said to find the critical numbers, the question said to find the relative extrema, which is based around the critical numbers. All right, so we still got to continue here. And the third step, now that we have found our critical numbers, the third step is to find the relative extrema, meaning relative min and max values, using that first derivative test that I spoke about towards the end of the last video. So let us demonstrate here how we set up this first derivative test. Okay, so first things first, let me rewrite our critical numbers. So again, we find our critical number Cn to be -1 and 5. I'll put in ascending order here. And to start the first derivative test, draw a number line. That's just a number line. That's a little crooked. Let me redraw that. Okay, so draw a number line. And the first thing we do in this number line is draw the two critical numbers that we found. All right, it doesn't really matter. The spacing doesn't matter too much. Just draw them in ascending order. So here we have, like, say, -1, and here we'll have 5. Okay, the two critical numbers that we found from the previous step. And then what we want to do here is, again, at these two critical numbers, for this case, these two critical numbers represent where the slope became 0. And what we want to identify is, we want to identify the type of behavior, the type of slope our function had before each of these two critical numbers, and after and in between. And to do that, to identify the type of slope, the type of behavior our function had before, between, and after our critical numbers, we just pick any values before, between, and after our critical numbers. And those values would be known as our test points. So pick any number before -1, like say -2, any number between -1 and 5, so that'd be like say 0, and then any number after 5, like say 6. All right, it doesn't really matter, any number. Okay, and then what we're gonna do here is, we're gonna take these test points, and since we're trying to identify the type of behavior, the type of slope our function had between these critical numbers and before and after, what we're going to do here is take these test points and plug them into the first derivative. So we're going to take our first derivative, evaluate it at -2, take our first derivative, evaluate it at 0, and then take our first derivative and evaluate it at 6. So again, we're not plugging them into the original function, we're plugging them into the first derivative to see what type of slope our function had before it touched any of these critical numbers. Okay, so what we're going to do is take -2, and again, plug it to the first derivative of 3x squared minus 12x minus 15. And again, we're going to show every single little detail, but we're going to plug in -2 into this equation. So 3 times -2 squared minus 12 times -2 minus 15. If you plug in negative 2 correctly into your first derivative, it should give you a value of 21, meaning at negative 2, based on the first derivative at negative 2, our original function had a slope of 21. So it had a positive slope, a huge slope of 21 here. Okay. Now, again, at negative 1 here, if we were to plug in negative 1 into our first derivative, since negative 1 is a critical number, and this is what we saw, this is what we got when we saw for the zeros of the first derivative, then that means if we plug in negative 1 back into our first derivative, it's going to give us 0. Same goes for 5 here. If we plug in 5 into our first derivative, it will give us 0 because again, these two numbers, negative 1 and 5, are the critical numbers, are the zeros of the first derivative. Okay. So, yeah, what we're trying to see is what the slope was, or what the slope is before and after it zeroes out. Okay, so here our slope is positive, then it zeroes out, and now we want to see what happens after that first critical number. So we plug in 0 into the first derivative. If we plug in 0 to the first derivative here, it's just going to give us negative 15. Meaning, before that first critical number, the slope was positive, then at some point it zeroed out, and then became negative. All right. But then at another point, it zeroed out again, and we want to see what happened to the slope after the second time it zeroed out. So we plug in 6 into the first derivative. So 3 times 6 squared minus 12 times 6 minus 15. If we evaluate this correctly in our first derivative, it gives us positive 21 as well. All right. Again, we're evaluating these points in our first derivative. We plug in negative 2, plugged in 0, plugged in 6 into the first derivative. Okay, so what is this telling us? This is telling us the following here. Before this first critical number, since the slope was positive, so we got a positive value. When we evaluated negative 2 using our first derivative, since we got a positive value, that means before this critical number here, our function was increasing. So it had a positive slope. So our function was increasing. All right. But then it hit this critical number, they hit the critical point at negative 1, where it zeroed out. So the slope became 0. Okay. But then between these two critical points, before it hit the second critical number, our test point resulted in a negative value in the first derivative. That means the slope became negative, indicating our function was starting to decrease until once again it flattened out. And after it flattened out for the second time, since the third test point gives us a positive value, that means after it reached the second critical number, our function started to once again increase. All right. So what does this tell us about our function, about the relative extrema? Well, this tells us here, since at this first critical number, since our function was increasing, meaning our slope was positive before it zeroed out, and then became negative, then that means that this first critical number, where it first zeroed out, we have a relative maximum. So we found a relative maximum at an x-coordinate of negative 1. Again, a relative max occurs when the sign of your slope changes from positive to negative, when your function has reached a high point and then starts to come down. Okay, so our function was increasing because it had a positive slope before this critical number, but then after that it became negative, meaning it started to come down. So at -1, we reached a high point, a relatively high point for this function. Okay, so our function pretty much was decreasing from -1 all the way to positive until it reached the second critical number at +5, where it flattened out and then started to come back up, meaning our function was decreasing, had a negative slope, reached the second critical number, and then had a positive slope. It started to increase once again. Meaning then, at x equals 5 here, our function reached a relative minimum. So we had relative minimum at x equal 5. Okay, because again, a relative minimum occurs when the sign of your slope, when the direction of your function changes from negative to positive. Your function is coming down, which is a low point, and then starts to climb back up. Okay, so here we have the two types of relative extrema, a max at x equals -1 and a minimum at x equals 5. But not done just yet. What we have shown are the x-coordinates of these relative extremas, but if we want to know the actual values of the max or the min, then what we have to do is take these two critical points and evaluate them using the original function. If we want to find the actual maximum y value and the relative maximum and the relative minimum y value of our function of x, then we had to take these two critical numbers where we found those relative extrema and plug it into the original function. All right. So to find the relative maximum, so again, we find relative maximum at an x coordinate of -1, but if we want to find the actual value, then we have to plug in -1 into the original function, not the first derivative, the original function. All right, which in our case was x cubed. So we're going to take -1 to the third power minus 6x squared, so minus 6 times -1 squared minus 15x, so minus 15 times -1, and then plus 30 to give us 38. All right, so if we evaluate -1 using our original function here, it gives us a value of 38, meaning our relative extrema is located at the coordinates of -1, 38 along our function. All right, and then to find the relative minimum, which is the same thing, except plug in the critical point where we found the relative minimum into our original function. So again, we found the relative minimum here, a low peak at x equals 5, a valley. So here we have a hill, here we have a valley. We found a hill at -1, we found a valley at 5. So we have found our relative minimum at x equals 5. So now we plug in find to original function. So again, we're going to take 5 cubed minus 6 times 5 squared minus 15 times 5 plus 30 to give us -70. So our relative minimum can be located on our function at the coordinates of 5 and -70. All right. So there we have found the relative extrema of this cubic function. All right. Let's see if we can visualize this. Let's go to our calculators and visualize this here. Okay, there's a G calculator. Let's set up our equation here. So we have x cubed, x cubed minus 6x squared, x squared, whoa, let me do that again, x cubed minus 6x squared minus 15x plus 30. All right, let me set the windows here based on our critical numbers and extrema. So our critical numbers were -1 and 5. I'll do -3 for the x minimum, 8, 40, x maximum. And then our y values were pretty large and small here, 38 and 70. So let me do the minimum. I'll do 75, -75, and then say 45 for the y maximum. Let's see how this looks. Yeah, there we have our function. All right, so again, from the left-hand side, from negative infinity, our function, starting from negative infinity, our function is increasing, but then reaches this high point here at -1 and 38. So here we have reached the high peak of our function at this critical number of -1 with our y value of 38, where we're at the maximum y 38. And then, so here we have reached our first critical point. And then after that, our function pretty much starts to decrease, starts to come down until it reaches the next critical point here at x equals 5, where we have a relative minimum of -70. And then after that second critical number, our function starts to come back up again. So here we have our high peak, the hill of our function, and here we have the low peak, the valley of our function. Okay. So there we have visualization of what we just found with those critical numbers. Okay. So again, we're trying to find here our hills and valleys of a function of x.